take a new landmark. The fourth railway bridge opened in 18 as the railway was unchallenged. With coals on the roads, road transit to have a future. Constructed to carry the editions. Time changes everything. People change, their ways change, and so their needs change. This has been the century of the technological revolution. Today, the river wears a new look. The machines have taken over. But a machine is just scrap metal if there's no power to drive it. So the Technological Revolution Board is continually adapting its program to the changing pattern of power demand. Electrical power is part of everyday living. Wherever we turn, it's there, at the flick of a switch. We take electricity in the home for granted, but for the housewife, it means a new and easier way of life. Electricity gives her a window on the world and an escape from drudgery. Well, someone has to make the tea. But it's a healthier way of life for all the family. Down on the farm, electricity is cutting labor costs. New applications of electrical machinery have increased productivity. You're just as likely to hear Farmer Mackenzie talking about the merits of infrared heaters as about the weather these days. A farm hand now is a technician who has to master a variety of new skills. Industry is making extensive use of prefabrication to meet the challenge of foreign competition. On the Clyde, electricity helps to build the best ships in the world. On the new industrial estates, light industry is turning out anything from typewriters to transistors. With electricity in the background, these industries are no longer tied to the coal fields for their supplies of cheap power. Heavy industry must be near sources of raw materials or near a port. Steel production is being increased by the use of new electric arc furnaces of up to 110 tons capacity. In the strip mills, automation makes further demands on electricity. So, where does all this electrical power come from? Water power is one of Scotland's richest natural resources. These are the Falls of Clyde. Energy from water power is harnessed by the turbo generators of the hydroelectric power stations which feed electricity into the grid transmission network. Another source of energy, coal for the thermal power stations, which are the main suppliers of electricity. However, coal reserves are not inexhaustible. Prudence and economic factors, too, give impetus to the search for other means of generating electrical power. The atom represents unlimited power. As the scientists probe the secrets of matter, increasing use is being made of nuclear energy as a source of electricity. The nuclear station at Hunterston is here shown under construction. Nuclear power stations such as Chapel Cross are even now feeding power into the grid network. The backbone of the grid has been the 132,000-volt system built between 1928 and 1933. Since then, the load has increased five-fold. This shows the present 132,000-volt network. At various points, substations tap off power and transform it down to the voltages required for different purposes. These 33,000-volt lines are taking power to a nearby town. Distribution at 11,000 volts is used to bring power to the countryside. Pole-mounted transformers along the route supply power to farms in the district. Finally, the low-voltage system brings power to the town dweller. In the city, power supplies are taken underground. Every second, the city devours electricity. Every year, the demand for electricity increases. Look into the future. Power demand is doubling every 10 years. This diagram shows the anticipated areas of heavy load in 1970. Glasgow, Fife and Sterling, air. To meet this tremendous increase in demand, new power stations are being built, but the additional generating capacity would soon place an intolerable burden on the overworked 132,000-volt network. To carry this additional load, a ring of 275,000-volt lines is being built to encircle the industrial belt of Scotland. The supergrid, as it is called, will take care of the increased generating capacity and also meet the future demands of the new areas of heavy load. This is the future supergrid. As we highlight Kincardine, we bring into focus the story of a striking engineering achievement. Here, the new supergrid spans the River Forth. Formidable problems arise when power lines have to cross wide rivers, and the Forth was no exception. Here is the proposed arrangement for supporting the supergrid conductors over the river. The design of the 500-foot high crossing towers was influenced by the width of the river, well over half a mile here, and by the fact that the lowest point of the conductors had to clear the water by 180 feet. In addition, each conductor weighs 16 tons. Work has already started on the site, and from now on the engineers have one aim in view: to get the huge conductors safely across the river to close the gap in the supergrid. Massive piling and foundation work is required before work can start on the crossing towers. On the south bank of the river, the ground is soft. The reinforced concrete piles slide down under their own weight to a depth of 40 feet before the pile driver has to take over. The site hums with activity as more and more piles are driven home at the corners of the 72-foot square tower base. Over the river on the north side, a special platform had to be provided to form a base for the crossing tower. A permanent pier to the river bank was also needed to give access for men and materials. The concrete platform is steadily built up. Reinforcement rods are shaped on the site. The skeleton of the tower base is sculptured in steel reinforcement bars and then cloaked with concrete. Blocks are sunk in the river to anchor the guy ropes of the derrick, which will be used for erecting the steelwork. The holding down bolt assemblies are lowered into the prepared cavities at each tower leg and concreted in. These are the roots of the tower, and from them the steel structure will grow until it reaches its full height. Steel erection starts with the positioning of the four main corner leg members of the first tower section. For this work, a 125-foot derrick is used. The secondary steelwork is assembled within the tower base. Each part is stamped with a code number corresponding to details on the erection drawings. Working as a well-drilled team, the steel erectors bolt up the panels in a remarkably short time. Both crossing towers are of similar design, constructed mainly of bolted high-tensile rolled steel sections, but the erection of this particular interest owing to its position in the river. The first section of the tower is completed. As the tower grows, the derrick is raised and supported by the steelwork already erected. When the derrick is in position, the second tower section is started. Kincardine wears a new look. Once the whalers sailed from here up to the Greenland seas. These men, now working on the center column of the tower, also know about ice and cold steel and driving rain. But the 15-foot square center column goes up. This will be used for raising parts and equipment for maintenance inside the structure because the wide base would make it difficult to get a straight lift from ground level. The steel erectors wear protective clothing. So does the tower steelwork. Every inch is hot-dip galvanized, and this coating of zinc prevents corrosion and reduces maintenance. The towers begin to take their final shape, and a new landmark is rising in the shadow of the Ojo Hills. Early spring is the deadline for stringing the conductors over the river, and that critical period is fast approaching. The men are now working on the top maintenance platform nearly 500 feet up. Down below, the winchman must be constantly alert. Section by section, the platform is bolted together. Up here, the wind is a bayonet. Teamwork. The job depends on the men, and the men depend on each other. At 45, they reckon a man's too old to work at these heights. With the top platform completed, everything is now set for the erection of the huge cross arms. That's 2.5 tons going up. These cross arms, 6 on each tower, will support the 3-ton insulator assemblies which will isolate the live conductors from the tower steelwork. Clamps down. The weather is something we can't tame. Work is curtailed on the site, but further afield, a vital part of the program is being carried out. At the National Physical Laboratory near London, tests are carried out on the insulators. Before being passed for duty, a complete 3-ton assembly is given a pushover test at over 1 million volts. Insulator strings in parallel make up each insulator assembly. As the assemblies go up, the construction of the crossing towers draws to a successful conclusion. The anchor towers, too, are completed. The first part of the operation is finished. Now the men on top brace themselves for the sternest phase of the operation, the complicated task of stringing the conductors over the river. Complicated because the conductors must not touch land or water at any stage. The smooth outer layer of the conductor, specially designed to reduce wind effect, must not be damaged by abrasion. However, the engineers have perfected a method of conductor stringing which meets these requirements. First, steel wire track and haulage ropes would be laid on the river bed, and then winched over the tops of all 4 towers. The track rope is fixed, but the haulage rope is operated by powerful winches. The practical installation problems are straightforward. Incidentally, getting the ropes wet didn't matter, as they were to be removed when the operation was completed. These 2 ropes will become the main haulage system during conductor stringing. And now we show how it was planned to get the conductors over the river. First, they were to be winched up to the north anchor tower and attached to the main haulage system. They would then be drawn up towards the first crossing tower, being supported by suspenders running at 80-foot intervals on the fixed track rope. At the crossing tower, the leading trolley and then the suspenders would be transferred from one side to the other, ready to take the conductor over the river and onto the south bank. The first conductor has now arrived on site. It was manufactured to an exact calculated length, and end clamps were fitted at the factory. The drum is jacked into position behind the north anchor tower. Soon the theories of the engineers will be put to the test. The long-awaited day has arrived. As the engineers leave their temporary homes, they think about the weather report. The radio forecast was good, but in these islands you can never really be sure. A construction crew assembles on the top of each tower. Final details are checked. The engineer in charge gives the order to start the operation. The front end of the conductor is hauled to the top of the north anchor tower, ready for the long pull over the river. The front end is passed over the special roller quadrant and through the anchor tower. On the working platform, a pulling plate is attached to the conductor. This, in turn, is connected to the leading trolley of the haulage system, and now everything is ready. The signal is given for the winch a mile away over on the south bank to start pulling. And away she goes, nice and easy. On its way, the haulage rope passes through a measuring device. At 80-foot intervals, a trolley is placed on the track rope and clamped to the haulage rope. A boom carrying a small bobbin is attached, and this supports the conductor as it travels up to the north crossing tower. Slowly, the giant conductor moves out into the north anchor span. The crossing tower crew awaits its arrival. To them falls the task of passing the conductor through from the anchor span to the river span. Pulling is stopped, and the conductor is temporarily attached to the tower by a bond wire as the leading trolley is removed and replaced in the river span. Next, the special cradle is tilted to receive the conductor. The bridle gate is swung open, the conductor introduced over the first rubber-lined wheel, and the gate closed. The conductor is then reconnected to the leading trolley, and the main winch starts pulling again. The long journey over the river span begins. Up to now, no problems with the weather. As each suspender reaches the north crossing tower, it is detached and replaced on the riverward side. Quickly, the men get used to the routine and faster progress is made. The speed and skill of the men can be judged from the fact that running speeds of up to 40 feet a minute were maintained as the conductor was hauled over. Soon the conductor is well over the river and coming up to the south crossing tower where the second construction crew is standing by. The engineer wants to check the leading trolley bond wire. Someone has to go out and inspect it. You can see why they're too old for this kind of thing at 45. Everything is in order, so the team repeats the whole process and feeds the conductor through the south crossing tower using another cradle slung beneath the top platform. These cradles have other important uses which will be seen later. Down now towards the ground and the second anchor tower. Back on the north side of the river, the trailing end of the conductor is coming off the drum. It passes over the rollers to the working platform. Holding tackles are attached to a quadrant plate fastened to the end of the conductor. By this means, the trailing end is supported clear of the north anchor tower. On the south bank, similar preparations are made to the front end of the conductor. A critical stage has now been reached. On both sides of the river, the conductor ends will be connected to powerful winches. When they apply tension, the conductor should become tight and free itself from the suspenders. The order is given. Both winches start to pull. the conductor hangs free over the whole of its length according to plan. The engineers agree that this is as good a time as any to break for a well-earned open-air lunch. The full purpose of the cradles, which support the conductor at each crossing tower. These are lowered until the conductor is at the correct level for attaching to the bottom insulator set. Temperature plays an important part in the calculations which the engineers make to determine the correct sag or dip of the conductor over the river. Once this has been established, the ends of the conductor are attached by linkage plates to the tension insulator sets on both anchor towers. Up on the cradle, the men are applying a layer of armor rods to the conductor at the point where it is to be attached to the suspension insulator sets. This is to prevent damage to the surface of the conductor. A corona bell is placed at each end of the armored protection. Now fully protected, the conductor is placed in the saddle and linked to the insulator assembly. One of the natural hazards which could affect the performance of the conductor is wind. Light winds could set up dangerous oscillations, so vibration dampers are fitted at all the conductor attachment points. The cradle is returned to the top of the tower for the running of the next conductor. A final operation is the fitting of arcing rings to the suspension sets on the crossing towers and to the sets on the anchor towers. The first conductor has made the 1.25 mile journey without damage and is now in position. The 5 remaining conductors and the earth wire were strung over the river in the same fashion. The engineers ironed out the practical snags so that each one had a smoother and faster journey. The construction crews cheated the weather to weave the heavy conductors through the anchor towers and the crossing towers until clockwork precision was attained. Not one of the huge conductors touched land or water at any stage. Five more times the red flags are raised as the big winch on the south bank starts to pull. 5 more times the engineers wait to see the conductor free itself from the suspenders. After that, the final stringing of the earth wire through the tops of the crossing towers was accomplished by the same means. Later, the track and haulage ropes were removed. The 275,000-volt overhead transmission link over the River Forth was successfully completed with time to spare. The gleaming new link in Scott stands as a tribute to the engineers who planned it and to the skill and perseverance of the men of steel who built it. But it is only a link, a part of the whole. It must be viewed against the changing pattern of electricity demand in South Scotland. The South of Scotland Electricity Board must forecast future trends and bring power to where it will be needed 10 years from now. The crossing is helping to do this by taking power across the river from the new Kincardine generating station. From there, the new supergrid lines are branching out to bring urgently needed relief to our power-hungry economy.